Hello everyone, this is Chahal here from Programming Club of IIT Madras, and I'll be giving out my solutions and hints for Codeforces Educational Round 149. As you can see, I was able to solve 5 questions and earned a rank of 123, and will be hopefully becoming a master in this round. So now in each problem I will initially be giving a bit of hints and then I'll be giving the solution so that if you were stuck on it you can see the hint, try again and then see the solution. So now moving to the problem. So problem A, a grasshopper on line. So here basically we have a grasshopper uh, that is present at origin and it has to reach some x coordinate x and it can take steps which are not multiples of k. So it can take any step which is not a multiple of k. So we need to tell the minimum number of steps that it has to take to reach the desired location. So one thing is that you can notice that only the steps of length not k, uh, steps which are divisible by k, it cannot take. So you can try to see which of steps are not divisible by k and you need to minimize it. So the ideal step length will be directly x. So you can see when we can take a step length of x and when we cannot. This is my hint. You should try it if you couldn't solve it from here. So now coming to the solution, basically, so as I gave away in the hint, so whenever x is not divisible by k, then we can directly take a step of length x and we'll reach our x coordinate x, as is the case in the last two examples. X is not divisible by k and we directly take a step of length x. So our step length is 1 and our a number of steps is 1 and our step length is x. Now say x is divisible by k. Now how do we choose the step lengths? So if x is divisible by k and it's given that k is at least 2, then obviously x minus 1 will not be divisible by k. So what we can do now is we can take two steps, one of length x and the one of length x minus 1 and then the next step of length say uh, so after this we'll take the next step of length 1 and this will take us to the point that we want to reach. So this is the basic solution and here is my code for it. So all of this is my template. Basically here is the main code. I'm taking two integers x and k as input. I'm checking if x is divisible by k. If it's not divisible by k, then I'm outputting 1x basically, and if it's divisible by k, then I'm outputting x minus 1 and 1 as I said. So we'll take a step of length x minus 1 and then 1 to reach x, as 1 is obviously not divisible by k for any k greater than 2. So okay, that was problem A. Now moving on to problem B, comparison strings. So this had a bit of an issue in its sample test cases during the contest. It was fixed later. So okay, coming to this problem. So basically this problem asks us that uh, so we are given a string of the form greater than or less than signs and we need to fill in numbers between them, which is basically our array A. Now we need to find out what is the minimum number of distinct elements. Basically the cost of any array A is the number of distinct elements in it. So we want to minimize the number of distinct elements. So we can work out the examples maybe and then come to the solution. So all right, these are the test cases, sample test cases, and okay, so the problem is just that we need to fill in numbers here and we need to, the cost of this filling will be the number of distinct elements in it and we want to minimize the number of distinct elements. So say without loss of generality we always start with 1. I mean if we get any other sequence we can shift it accordingly and we'll just, so let's say this is greater than, so we'll put in 2 here, then 3. Now we want less than, so let's put 2 here and 1 here. So as we can see we can do this in 3 distinct numbers. Similarly the next test case is same as the above one, just that say we start with 1 then 0 then minus 1 then 0 then 1, again 3 numbers. Now coming to this test case we start with 1 0 minus 1 minus 2 minus 3 and minus 4. We had a total of 6 distinct numbers here and starting here 1 greater than this 2, then again 1, then 2, then 1, then 2, then 1, then 2. So this will be two numbers. So as you can see, these are exactly what the test cases say. So now you might be tempted to think that we can just start with one and keep on decrementing according to the question and get an answer, but that is not correct. Why? So if anytime we have like less than signs and more number of greater than signs, then we run into a problem. For example, consider this test case. So we have okay, 1 second. Yeah. So we have two greater than signs, then one less than sign, and then again two greater than signs. So if we follow the strategy that we have done above, we'll end up filling it as 1, 2, 3, then 2, then 3, then 4. This is four distinct numbers, while you can fill it in three distinct numbers by using this strategy. Like, yeah. So, yeah, this way. So, here we're using only three distinct numbers. So I feel like this test case is my hint. If you weren't able to solve this till now, you should try to think on why your code fails on maybe this test case or some related test case and solve it further. Now, coming to the solution. So basically, the greatest number of least number of distinct numbers that we need is the longest sequence of either greater than or less than signs plus 1. Like here it's of length 2, so we have answer as 3. Here it was of length 5, so our answer is 6. Here there were 2 of length 2, so our answer is 3. Again 2 of length 2, answer is 3. And here the greatest length is only 1, so our answer directly becomes 2. So essentially we just need to find out the length of the longest sequence of less than or greater than signs. And that will be enough to solve our question. So if you want to see its implementation, that's here. So again, what we have done is we've taken the number and the string as input. Then we have initialized our answer as 2 because we know that the string length is at least 1, and so there will be at least two distinct numbers required in each case. Now I've used a boolean variable increasing to tell me whether currently the sequence is of increasing symbols or decreasing symbols. So currently I've set it to false, but if the first symbol is less than, I've set it to true. And then in the loop, I'm just checking the condition that if it's increasing and if the symbol is greater, then I'm increasing count and increasing answer, recalculating answer correspondingly. If it's greater and it's decreasing, then I'm resetting count to 2 and changing increasing to true. Similarly, the other cases for the inverse. So you can check this out. It was a nice problem, I felt. Now coming to the next problem, problem C. So, all right. In problem C, basically, we have been given a binary string wherein some alphabets are replaced by question marks, and we have to decide what we want to fill in the question mark. Now we need to fill these question marks such that the number of operations required to sort the string is the least. But we have some certain constraints on sorting. So our constraint on sorting is that we can choose a substring and we can reverse it. Okay, so essentially our strategy will be something like this. If that substring has ones in start and we reverse it, then it becomes zeros and ones. So we'll work out the sample test cases. I'll work out the sample test cases, give you some observations. So all right. So basically, what we can do is, if say we have some string like this, all right, we can just apply one operation on the whole string, that is reverse the whole string, and end up with the zeros in start and then the ones. So essentially, what is happening is that whenever we have some zeros followed by 1, if we swap it completely, we get the like if we have any ones followed by 0, if we swap it, we get zeros at start, 1 at back. So essentially what is happening is that even if we have a group of ones, say instead of 4 here were infinitely many ones, or even instead of zeros there were many zeros, in one switch we are able to sort the whole thing. So essentially it doesn't matter how many ones or zeros are there. What matters is their components. Like if we have something like 0 1 0 1, Then we can sort this in one move by just swapping this string, this substring. Now instead of this, if we add 1010, we can do this in, say, like, so I think in one swap we cannot do it, obviously. So in two swaps, if we want to do this, we'll first swap the last two. We'll end up with 1001, and then we'll switch, reverse this whole string, and we'll end up with 0011, which is the sorted string. So essentially, it doesn't like, our count of this thing matters on how many distinct, like how many switches between 0 and 1s are there, like the number of switches it requires. And if we want to minimize that, we want to keep it as less as possible, like the switches between 0s and 1 should be as less as possible in the string. So what based on this, you can think of an optimal strategy, like this is my hint, sort of, that hint and observation, that the number of swaps only depends on the switches in the string, and you can try it on from here if you can get an idea. Now, so coming to the solution, so the best approach to minimize the swaps is just take every question mark and just make it equal to the number on its right. So here we have 0, we'll put this as 0, the number on its left or right. So here we have 0, we'll fill these two as 0 and this one as 1. Similarly, we have 1, this one is fully filled. So if we have 1s here, we'll just fill these question marks with 1 and this one with 0. Similarly, here we'll fill with 1, here also 1, here say we can fill with either 0 or 1. So say 1 or 0, either in, without loss of generality, and we'll get the string required, which requires least number of swaps. So essentially, this is the algorithm, that for every question mark or set of question marks, you see what is the number on right or left, 1 or 0, and accordingly you assign that number. If both are same 1 1, then you assign 1. If both are 0, you assign 0. If it's 0 1, you have the choice to assign any you want. So this is essentially the solution. As you can see, these are the strings that will match as I showed here. Now coming to how I coded it up. So now I had to make a choice in those cases. So what I did is I just always made it equal to the one on the left. So firstly, I've taken the string as input, then n is the size of the string, and I've made a bool same. So this is just to ensure that in the case that the entire string is filled with question marks, so I'm checking whether the entire string is filled with question marks or not. If it's completely filled by question marks, I'll just output all zeros. Alright, now say it's not filled entirely by question marks and there are some question marks, some ones, some zeros. So here I'm maintaining the least recently, like last element that I saw, which wasn't 1 or 0. So if last element hasn't been visited, like if it starts with question marks, I can't assign number to the initial question marks because I don't know what the element to left of them. So I skip those elements. Then if say I get a question mark and last is assigned, then I assign that to that instance of s of I. And accordingly I'm switching the last here. So now say the initial part was like if the initial part had question mark, like the start of the string, then I need to handle that separately, as I need to find the element on right of them and then assign it. So that is exactly what I've done. I've initialized last to -1 again. If there's a question mark in the start of the string, s of 0 is the first character of the string. So now I'm going through the string, searching for the first character that is not equal to my question mark, and accordingly I'm setting last equal to 0 or 1, and then I'm setting all values from s of 0 to that index as 0 or 1 accordingly, and outputting the string. So this is essentially enough for the question. Yeah. So that was it for this question, problem C. Now moving to problem D. So problem D is about regular bracket sequences. Regular bracket sequences are basically sequences which can be filled with numbers and symbols so that it makes sense as an arithmetic expression. Like it is essentially nesting of arithmetic expressions. So one like property of regular bracket sequences is that if we take a prefix sum of open bracket and close bracket, then open bracket minus close bracket, the number of them, then that is always greater equal 0. Like if we see here, it's initially 1, then 0, then again 1, then 0, then here it's 1, then 2, then 1, then again 0, and so on. Now they have defined a new term as a beautiful sequence. So beautiful sequence is either a regular bracket sequences, or if we reverse the characters, then it becomes a regular bracket sequence. And now we've been given a string. So the problem is basically that we've been given a string, and we need to use the minimum number of colors to color the brackets such that all the brackets of one color form a beautiful string, right? So we'll try to work out a few examples and see what we observe. So here, yeah. So these are the test cases. So yeah. Okay, so I'll just here if we see, this one is, if we see the second test case, it's already a regular bracket sequence, so we just need one color, we can just color all in one. Similarly, the third test case is also a beautiful sequence, because if we reverse it we get a RBS. So again we need only one observation, one operation here, one color here as well. And if we see the last sequence, then it has an unequal number of open and close brackets. Like whatever we do, what we can notice is, if we have a regular bracket sequence, then number of open brackets equal to number of closed brackets. So the same will be true in its reverse also. So essentially we need this condition to hold in the entire string. If this condition isn't holding, then we cannot nest that, color that properly. So for this the output will be -1. Now coming to the first test case, so let's see. So if we start from, if we see the number of open and close brackets are equal, so now we start from here and we can see that this portion of the string is a regular bracket sequence, and this one, if reverse, is a regular bracket sequence. So essentially what we can do is, we can sort of have a running sum or a prefix sum of open minus close, or close minus open, as you want to say it. And whenever it, so if it's negative over a certain sequence, then we know that it will have to be something like a reverse of a bracketed sequence, like here. So here if we see, the prefix sum is -1 and then 0, 0 -1 0. So essentially what we'll do is, we'll use this prefix sum of open minus close. So this will tell us, if it's positive or positive, then we know that it's a regular bracket sequence, and to become negative it has to reach 0 at a point. So whenever it reaches 0, after that it's negative. So that sequence we can say it's a reverse of a regular bracket sequence. So essentially what we'll do is, so essentially we can divide the string, any string given to us. Say this is the string to you, like, so we have something like, yeah, if you see, we can divide the string into three parts, so that this part is a regular bracket sequence, this part is a regular bracket sequence, and this is reverse of a regular bracket sequence. So essentially what we are able to do is, for any string we are able to divide it into parts that are regular bracket sequence and that are reverse of regular bracket sequence. And now we wish to color them. So like what someone might do is use one color for the first part, second color for the third part, and third color for this third part. But essentially we can do better. What we can do is, for all sequences that are regular bracket sequences, like, so we can color all of them in one color, and for all which are, say, reverse of regular bracket sequence, we can color them in the second color. So essentially this is what I've done. Like, I've colored the reverse of regular bracket sequence in color 2 and used color 1 for regular bracket sequences. So if you want to see my code, that is here. So I've taken the string as input, and firstly I've checked whether the number of open and closed brackets are equal. If they are not, then I'm directly outputting -1 and returning. Now whenever it's not -1, we can always have an answer. So I've used mode as a temporary variable just to tell me whether it's a regular bracket sequence or reverse of regular bracket sequence running, like is the running some positive or negative. And essentially count is maintaining my running sum. It's initially 0, and I'm setting all variables in answer. Like answer of I will be either 1 or 2 depending on whether it's a regular bracket sequence or reverse of it. And if it's open bracket and our mode is 1, that is we are running in regular bracket sequence, we increase count. uh, if mode is 2, then we decrease count, or if count becomes negative, then we change our mode. Similarly, if mode is 2 and count is positive and we encounter a close bracket, then we increase our count. And essentially that's the idea. And just one case that if the number of, like if the complete sequence is a regular bracket sequence, then we just need to output one color and all in one. If the complete sequence is reverse of a regular bracket sequence, we just need to output one color and that will be one all. So this is what we have checked here. Like this was a corner case that my implementation was missing, and then we are just outputting 2 because in worst case we can always do in 2 colors, and we are just outputting the answer as it is. So it was an interesting question, uh, quite a bit of scope of making silly mistakes here in the implementation as well. Now moving to problem E. So problem E, play of fixing. This was a pretty interesting question. I found it daunting at first, but then I went on with it and thought about it, and I could solve it. So I'll go with it. So essentially, there are two per cave teams participating, and what we want is we want to rig it such that we have team one as winner, team two reaches final, team 3 and 4 reach semi-final, and team 4, 5, 6, 7, 8 reach quarterfinals, and so on. So essentially, we want any team with like corresponding number of binary dates should reach that much rank. So for that, basically, so it's essentially sort of a tree-like structure where all teams are there at the bottom, and successively the number of teams is halving. It's like a normal tournament, knockout tournament. So now what they have done is that so here basically we've been given the setting of the tournament, like what's the initial setting and what all teams haven't been placed. Basically we need to place them and count the number of ways to do that so that our rigging is successful. So the input is given in a format such that they've given which team has the seed I. Like here, team 1 has seed I, team 1 has seed 1, team 2 has seed 2, team 3 has seed 3, team 4 has seed 4, and so on. And if it's -1, then that seed is unassigned. Seed is basically the position in the tournament tree that the team is taking, and it's given to us that the team with the smaller number is stronger, which is why team 1 will always win. So essentially, the stronger team will beat the bigger team and move up. So now we just try to solve a few test cases and see what we can see. So the first test case, there are 4 teams. So 1, 2, 3, and 4. So winner of 1, 2 will be 1, winner of 3, 4 will be 3, and winner of 1, 3 will be 1. Now we can clearly see that all places are fixed and we are not getting 2 into finals, so it's not possible, and so answer here would be 0. Like there are 0 ways to rig the tournament in that way. Now coming to the next test case, we have 1, 3, 4, and 2. So here again all numbers are fixed. So winner of 1, 3 will be 1, winner of 4, 2 will be 2, and winner of 1, 2 will be 1. And as we can see, this is following all our rules. 2 is reaching finals and 3, 4 are reaching semi-finals. So this is one way to do it, and all numbers are fixed, so there's only one way to rig the tournament in this test case. Now, so first 2 test cases are done. Now coming to the third test case. We have 2 places, both are unassigned, and we need a winner. So essentially whether we put 1, 2 or 2, 1, it doesn't matter here. Like, so essentially we have 2 choices here, and in both cases we are satisfied. So the answer for this test case is 2. Now the next test case where there are 4 places, so yeah. So here we'll have 1 at the top always. Now we can decide whether 1 comes from left or right. So there are two choices for that. Say we, without loss of generality, say we take 1 as left. So 1 comes from left and 2 has to come from right then. Now again in this level, again we have two choices whether 1 comes from right or left. So again 2 without loss of generality, let's say it's come from left. Again we have two choices for 2. So there again we get a 2. And now we have two choices for positioning of 3 and 4, whether which of these two places they take. So essentially it's 2 into 2 into 2, so 16. Now we'll just consider this test case 1 the last test case. So in that there's only one team and it's fixed to be 1. So there's only one way to do that. It's just a corner case that will come up in the code later. Now if we take this test case, the only one left. So here we have 8 teams in the match and only one place is fixed, that is this one, S2. Okay, so essentially we'll be having something like this as our tournament tree. Yep. Now okay, so what we want is for 2 to, oh sorry, I didn't change my page. So yeah, this is essentially the tournament tree given to us. Now okay, let's see the, so according to the question we want 2 to reach semi-final, to reach finals. This is the finals basically. So let us just place 2 in all of the matches till there. That is, 2 has to win these matches in whatever placement we do. Now we'll start placing numbers. So uh, here in bottom we need to place 7 numbers in total, and in the top we need to place only one number. So it's optimal that we start from top and go down. This is what I felt. So we'll just place 1 at the top because there's only one choice to do that. Now here we see the below level. So 2 is filled here, so 1 has to come from here. Now in this level again, 1 has two choices whether to come from right or left. So let us take left, and okay, 1 has two choices. That's why we have 2 in our answer. Now again 2 is fixed to come from left, so we have no choice there. Now in the place, now we want 3 and 4 to reach semi-finals, right? So we'll have to place them in these two spots. Now essentially it doesn't matter whether we place 3 to left or 4 to left. So essentially we have two choices again there on whom to fill in left and right, like what order to fill in these vertices. So let's say we fill 3 then 4. Okay, that's good till now. Now again, now coming to the last level. So here again in 1 we have two choices whether it comes from right or left. So let's say it comes from left. Again we have two choices in 3. So let's say again it comes from left. For 2 it's fixed. Now for 4 again we have two choices whether it comes from left or right. So again there comes a 2. Now once we have placed these, so we have 4 remaining numbers which are 5, 6, 7 and 8, and we need to place them in these 4 spots. And it essentially doesn't matter which order we place them because they're obviously greater than 1, 2, 3, 4. So essentially there will be 4 factorial ways of ordering them, n factorial for n numbers. So this whole thing gets multiplied by 4 factorial. And if you calculate this whole number, it comes out to be 768, which is the same as the one in our test case, right? So essentially what did we, so essentially the solution is in crux of this test case. This is my hint for this problem. You can try out how we solve this test case, like go through my solution of how I solved this test case and try to understand and code it up. Now I'll try to explain how. So basically what the strategy is. So what we'll do is initially we'll find out which all numbers have been fixed already, like 2 was fixed here already. So for those fixed numbers, we'll take them in the tree as much up as we can, according as much up as we have to take according to the required condition, that basically 2 should reach this level, 3 and 4 should reach here, 5, 6, 7, 8 should reach here, and 9 to 16 should reach the next level, and so on. So accordingly, we move the number that much up, like in each of the levels. We marked it in each of the levels. Now, once we have marked it in each of the levels, and there are no conflicts, like say we didn't have something like 2 here and 1 here, like in our initial tree, we didn't have something like this. So yeah. So if we had something like this, say 2 is here and 1 is here in the initial, okay, wait, again now. So say 2 is here and 1 is here in the initial tree that we had, then basically the problem that we run into is we want 2 to reach this level and 1 to reach this level. We will make them in this, so 2 and 1. Now 2 and 1 have to fight between them and only one of them can go up. So obviously we will not be able to rig the tournament as we want, and so there are 0 possible ways to do it in this case. Okay, so now the first part of the solution is basically take numbers up as much as we can. The initial numbers that are already given to us, which are not -1. So now once we have done this, the second part of the solution is placing the remaining numbers. How are we doing that? So we are following a top-down approach for that. We are placing 1 first, then we are going to next level, then we are saying if all numbers are placed here, again we go to the next level, 3 and 4 were in place, we place 3 and 4, then we go to last level, and then we place 5, 6, 7, 8 and so on. Okay, so essentially what is happening now is whenever say we go to a new level, we find out which numbers are in place there. So whichever numbers are in place, there are say k numbers, like say some I numbers are in place, there are I factorial ways to arrange those numbers. So for each level, this I factorial factor will come in. Now once we have placed the numbers, we need to propagate them down. Now while propagating down, we'll either have two choices or we will have only one choice if some number is filled up, like here 2 was filled up, so we had only one choice to move one down left. So we will have either 2 or one choice to move every number down. And in case there are no choices, then that means the answer is 0, obviously. So essentially this is my solution, and now even if you get the solution, I know it is a bit difficult to implement it because you need to use the concept of trees and how to go up and down. So if you want to see it, then I'll show my code. This is basically my template to calculate value of any factorial mod the number m. So now we've taken the k, which is the number of levels in the basic tournament, and n is the number of players, 2 per k basically. And now we've created a tree. So this tree has been implemented as a vector, which is of size. If there are n elements, then it's basically if there are 2 per k elements, its size is 2 into 2 per k minus 1. Now you will ask why it's this number specifically. So why this number? Because 2 per k plus 2 per k minus 1 plus so on up to 1 sums to this number. So essentially we are capturing all levels of tree in this one vector. Now here we are just taking the bottom level of the tree as our input. Then if if there are only one level, like k is 0, then we are directly outputting 1, which was our corner case here, this test case. Now so what we are doing now is we have just this is basically where we go from bottom to up, like we take every number and put it as much up as we can, and we are doing it level wise, like we are starting from the lowest level, propagating all of them above, then propagating them one level up, and so on. You can go through my implementation here. So essentially I'm going through all nodes, checking if they are -1 or not, and checking if they're children and so on, and taking them up. Now after taking them up, I'm checking if I'm going down. So now I'm going down. Essentially here basically, as you can see, I'm counting the number of elements that I have to add, like it's getting in count. So that much factorial I'm multiplying, and then here I'm doing multiplied by 2 if both I have choices of going left or right. And essentially that's it. Just for the last level I need to do separately because my loop goes till level k minus 1, and then I'm just outputting the answer. So essentially that's it. I felt that concept wise this problem wasn't that difficult, but the problematic part here was the implementation and the length of the problem. Like the problem statement was very long, and that feels a bit daunting. But otherwise I felt it was a simple and elegant problem. So that was it from my side. I would love to hear your feedback or any queries you have in the comments. Feel free to reach out to me. Thank you.